Are you guys all okay with recording? Now, listen, usually what I tell my students is that they should go up to the 3 dots in the upper right-hand corner, pull down, just name themselves their first name. But because you guys are presenting, I would actually like you to make sure that you're named your full name so that people know who you are, if that's okay. Can you do your 3 dots, go down full names for everybody? That would be really wonderful. Great. Wonderful. So we've got 3 people. I'll wait about 2 more minutes before we get going. But while we're waiting, and at that point, I'll have you guys introduce yourselves. While we're waiting, I might as well introduce the group to you. This is the Biodesign Challenge class. This is Rutgers University, Camden. This class is hosted in the Department of Visual Media and Performing Arts, although there's also a section of the class that runs in the urban planning, urban studies a section of our curriculum. So the students are coming back to join us. And basically what the class is it's an international curriculum for art and design students in biodesign, and it's sort of geared towards getting new ideas into the space of biodesign. So at the end of each year, the projects from this class, we vote on one of them. We actually go and redo the project, and then the project's presented at New York MoMA in front of a panel of 60 judges in the space of biodesign, and it's a big deal. It's wonderful. They also have a big exhibition in New York, and it's really fun. So this little group has done amazing things, and usually the biodesign projects that they're doing are in response to the needs of Camden, New Jersey. So I don't know if you guys know anything about Camden, New Jersey. It's a city of 70,000 people. It now has 1 grocery store that has fresh produce, so it's considered a food desert. It's got serious water quality issues. It's a post-industrial urban landscape, so it also has a lot of problems with pollution. And I love it. Camden is just the most wonderful place on earth as far as I'm concerned, because the people here, it's really like a do-it-yourself. People do not depend on a market economy. It's got more community gardens than any city on earth. It's got amazing community resources. So we are rich in community. And one of the really cool things about it is the projects that come out of our class actually respond to needs in the immediate community. So in any event, that's a little overview. People are going to be sort of joining in probably over the next 2 or 3 minutes, and I'll be admitting them. But would you guys like to introduce yourselves? Nedko, would you like to go first?
Yes, I first want to say that I just 3 or 4 minutes, I finished my last class. I'm a high school teacher, AP Art. And for this, I'm so formal, so sorry for that.
We should all have our ties on. No, we should. I should have. You don't know this, but everyone in the class with their camera off, they're all wearing a necktie right now.
So okay, I will not feel like uncomfortable this way. I'm doing my thesis in New Jersey City University, and my let's say main idea is related to the water problem. And I started about a year and something in some project. And in the project, I will introduce these things after that. I have a small PowerPoint here to make this, but I make a project that was really pointing to how bad is the situation. And the project was so pessimistic that at the end, when I showed it to my professors and my colleagues, I decided to make an opposite project that is actually positive, and it's looking for something that gives a light in the tunnel. And I start carving an internet, who is working in what, so who is making these changes and in the world. And I find out one of the first thing, let's say the first 3 things that I was impressed was this luminescent metal organic crystals, metal organic frameworks that these guys from Rutgers under the Professor Lee, they make it, they create it, they design it. And then I wrote Simon a letter about 3 months or 4 months was, and Simon was so great that he sent me practically the base for what I'm working now. And it's that molecule of this crystal. So what it's about, maybe they will explain a little better about, but I'm just trying now in this project to give the second part of, which is the positive part of the problem with the water. How is possible that we have some small thing that put in the water and there's no more heavy metals there? And sometimes I'm surprised that we have the solutions, we have the people, we have the knowledge, we have the technology, and there's something that is not happening. And that's my artwork actually directed. I want to make some awareness that there's solutions, and maybe more people will start talking about these amazing discoveries, and then something could change. So that's actually the main reason for all this. And again, I appreciate very much what you, Elizabeth, did for this, because without you, I never will see that Simon is a living guy, really, and Everest as well. Okay.
That's wonderful.
I feel so excited.
Great. So perhaps our two other visitors could just in a sentence tell us who they are. Simon, do you want to go first?
Okay. As you can see on the screen, my name's Simon Teat. I'm a staff scientist at Lawrence Berkeley National Labs, and I work on, I'm an X-ray crystallographer, and I work on the advanced light source, which is an electron accelerator. So it accelerates electrons to 99.999% of light speed. And every time they go around a corner, they give off electromagnetic radiation. So everything from the infrared all the way through to the hard X-ray. And it's a much brighter source than a lab instrument. So we get a much stronger source of X-rays, so we can look at smaller and more difficult crystals.
That's fabulous. Wow.
I don't know whether you know much about it, but if you take a regular array of an object, so if you think of something like a brick wall going off infinitely in 3 dimensions, if you hit that with X-rays, you will get a pattern, and the pattern will tell you how it's constructed. So at the atomic level, we have a combination of, in this particular case, of the MOFs, metal centers, and then linkers. And by hitting them with X-rays and looking at the pattern, the positions of the spots and their intensities, you can back calculate where the metals are and where the linkers are. So you can then see this microporous structure. Or accurately, you can see the average structure.
Wow, that's amazing. We're actually doing microorganisms right now in this unit. We just spent the beginning of class looking at these little tiny objects. So that's awesome. Well, welcome to our class here. I'm in New York, but this is Rutgers University, which is New Jersey. And I did my grad work and actually taught at Berkeley for a little while. So Berkeley is near and dear to my heart. Our other guest, is it Ever? Is that your first name?
Hi, yeah, that's pronounced correctly. Can you hear me?
Yeah, we can hear you.
Oh, sorry. Yeah, that's pronounced correctly. My name's Ever Velasco, and I'm currently a PhD student from Dr. Jing Lee's lab. My work relies mostly on the design and synthesis of metal organic frameworks. We use them for a variety of different applications. My main focus is either the luminescent detection of organic species, or dangerous, hazardous organic species, or also absorptive separation of isomers. So we do a lot of work also on hydrocarbon separation. So as Simon said, these materials are actually quite porous, and we do have some control over how what size the pores are. And we can separate mixtures of isomers through these materials, which is also quite interesting.
Wow.
So yeah. So that's basically what I work on in Dr. Lee's lab.
Awesome. All right. So, and you're joining us. You got your mask on. So I'm going to guess you're on campus. You're at New Brunswick,
yes,
right?
Yeah, I'm currently
Yeah.
in campus now.
Yeah. Well, hey, welcome. Well, that's wonderful. Okay. So, hey, Nedko, would you like to begin the presentation?
Okay. So actually, I will simplify a little bit because of most of the things we're taught. I will share a screen a little bit with something that I have here.
Okay, and really quick, I just allowed multiple participants to share. If you have any video that has audio, do you have anything that has audio?
Yes, I have audio as well.
Oh, okay. So listen, do you know when you open up the Zoom, you have to check the box for sharing audio? Are you good for that?
Let me see.
I never find it there. Nedko, when you go to share screen, you know, it opens up into a white screen and then you can choose which one you want. Down in that box in the lower left-hand corner, there'll be two little tiny boxes and one says share sound. You just need to check that for sound, for audio. So you might want to get out of screen share for just a moment.
Let's see. Stop sharing.
Okay. Now, when you go to share, it'll open up a white window just for you to see. So you have your choices. In that window, it's down in the lower left-hand corner.
Just a second. Okay.
This is great. I made all my students share their screens today for audio, and we're all learning where to check and where to get our right.
Just a second. I'm actually a Blackboard guy. I'm using everyday Blackboard as crazy. So Zoom is like something just for this kind of things. So it's start share.
Okay, but don't select the item yet. While you're still in that big white window where you can select different windows, different documents. In that white window, down in the lower left-hand corner is a little tiny box. There's actually two little boxes. The first one will say share sound.
Okay, but you can hear the sound from my computer as well.
I can hear you speaking, but if you want to play any audio or video with audio, you have to have that checked.
I really don't want to do anymore this delay that. I will just explain the things. It's maybe I will send you after that
oh, perfect. Okay, great.
You can do with them.
Okay.
So good. I've shared this. Sorry guys for that.
It's okay.
I'm trying. Okay. So good. So actually, can you see my screen?
Perfectly.
Okay, good. So I'm going through here just to make the slideshow view. Just a second, slideshow from the beginning. Good. So visual artist, teacher, writer, researcher, etc., etc. I don't think that this is so important, much more than we have here. So what are facts? For the kids, that's important. 200,000 people die in the United States from waterborne diseases. And that looks like a trivia because you say, okay, they die for anything, but from water they die. Most of these people are under age of 20. And about 6 million in Earth. So it's actually every year it's a war. It's a war and big war. And even though it seems like something that is not so important, it's maybe the most important part of the problems that exist, the most important problem in Earth that exists. So part one was the secret garden that I just talked about this, and the part two is Absorbsin, which is the invention that I create for the name. I don't know if ever and Simon will accept that, but I just try to make a project that has something related with this, but it has a name. The name comes from absorb and sin, because it's like a miracle. a miracle that absorbs our sins. You know, it's like the pollution of the water is our sin, actually. So this is the idea about, and this is the second part of this project. And the first part was, I shared this with Simon. I'm not sure that ever you received this. The first part was a time lapse, 20-something days time lapse of 10 the same plants in 10 different waters from the three best water regions United States and the 7 worst. And I just observed what's happened with these plants with, for example, how fast they die from the water from, for example, from Newark, which is here near us. And that was the first part of the project. So these are here, the water, it's water devices that are sent to these 10 different places in the United States, and they return 2 liters of water from there. So actually inside I put that water from this from these water recipients. So the installation was like that, talking about the problem. The biggest problem in this moment is that it's even racial inequality in where the water is distributed, and that was the initial of my actually discovery, because when I start like checking the data, it seems that coincides that regions with other problems, social problems, they have the worst quality of water. And this is the video actually of this hidden garden. It's long video, so I will not.
I'm hearing it though. Nedco, I can hear some of it.
I know, but you know what's happened, that I want much more, maybe the students, and I can send to everybody this PDF if you're interested after that. I much want.
That'd be great.
I don't want to talk only. I want everybody else to be. Yeah. So this is here about this. Inside of this is the lapse, the time lapse, with exactly how this plant were dying. And I actually presented this to the audience in Jersey City University, and the comments were like really dark. So I tried, because of this, to make the second part of the project. So this is actually the end of this video. These are the real places where I received the water. These are the demographics of the population, and these are actually the contaminants that officially are announced in the data. So you can see later inside that that we have some social problems in the distribution of quality water as well. So here is the second part of the project, the Absorbsin. And actually, this is a photo that Simon did and sent to me. I am sure that he did this. And this is the first inspiration that I get after that to look behind and inside of that. So this is how this looks. The LMOFs 262 or 263 is this, Simon? I'm not sure.
To be honest, I can't remember which one it is off the top of my head now, but actually this came from Jing's group. As part of the information they send me to do the crystal structures, they send me pictures of the crystals. Okay. So I just happened to have it, and I sent it to you. It's great.
Nedco, I have a fast question. What's the magnification on that?
This is actually 100 microns, is like that.
Okay.
Nano, what? 100 microns?
Yeah, the little red thing in the middle by the crystals says 100 microns.
Wow. Okay.
So this actually are what Ever was saying, that these are like the structures that are so porous inside that they can trap the metals. He maybe can speak a little more about this and how the photo was taken and what we see here.
So, as I said, the photograph was taken on a microscope in Professor Jing Li's lab. What you're seeing here is clusters of crystals. If you look near where it says 100 microns, go up and slightly to the right, you can then see each of the, you can see the sort of individual crystals. Down to the bottom right as well, you can see, you know, the oblong-shaped crystals all coming from a common center where they started to grow from.
And Ever, I have a question. Is that in a process of exactly capturing? So this black around is water with heavy metals?
So actually, these are just the single crystal images. So when we make these materials, the only way that we're able to obtain the actual structure of these materials is through a single crystal that we then sent it to Dr. Teat. And Dr. Teat can then give us the actual atomic arrangement of every single individual atom inside the structure. So then in the manuscript, in the actual paper, we have a figure. I think it was like let me double check. It was figure 1 that actually shows all the data that Dr. Teat sent to us, and we just draw it in a different way that makes it look a little bit more appealing. But in that structure, you can see the actual atomic arrangement of all the atoms within the actual material, so within the actual crystal, and you can see the actual porosity that the material has. But here's just the single crystals of the as-made material. So when we pull this out, this nothing has been done to this besides synthesize it.
Thank you. So I can go in the next one here. And this is something that I started. This is what Simon actually, this is the molecule of the crystal, the real molecule of the crystal produced in a software. And I received that in this CCDC beautiful 3D renderer, and I start like carving there. And I start producing from this molecule something that is part of my project, how to make it, how to modify it with the language with the visual artist. So what I was looking here to do is to find out, to make it like a living creature that is creating something. I understand that the two scientists here say how living creature is nothing like this, but when you're talking about something so important, something so amazing as scientific discovery or design, scientific design, people can imagine the function through the form. So I had to look in the same software to some way of re-elaborating. I will be very happy if I hear some opinion from you guys, Ever and Simon, from your point of view, how from your eyes, how this, I mean, what is your opinion about that? That's something that the kids will maybe understand, how we see the same thing from the different point of view. I don't know, something like that. Maybe later. Okay, I will go later. So I don't want to, if you don't want to. So this is how I try to make this look like something that is giving birth, something that is giving like second chance for for life, something that will produce life. So that's the idea about re-elaborating this this molecule that you sent me. So the other thing that I did related to this is to find out all the chemical structure of this and pass this chemical structure to one software that make it in sound. So I practically try to see how sounds this this crystal, this molecule of the crystals, if I put this atom structure, and I have some examples here. This is a software that can do that. You put just data there, and it produces a sound. And actually, currently, I have a collaboration with a composer in Miami. It's called Jorge Sosa. He's a professional composer. That's his work. He has some of these files that I produce, and he will create. So this is a small part of these two groups. I have the bonds, the data. I have also the heavy metal water. I find out a formula, again, with collaboration with people who are working in this. I receive it's a very long formula of what the heavy metal water looks like. So I just put it there again in this software. So my idea for this artwork together with Sosa is to make the crystal interact in a musical, I don't know what will be. He's the one that could be a, I don't know, classical music. They call this fuga, like from the time of the Bach, or some different, I don't know what the form, but they will have these two ideas about so this is the, sorry, I didn't have to do that, but just for a second. Just for a second.
So, hey, Nedco.
Yeah.
While we're waiting on that, we do have a question from the group. A question just straight in.
Okay.
What does the crystal actually do in water? You said it takes out heavy metals. If you put it in water, how long does it take to take the metals out? And is it safe to drink the water with the crystals in it?
I think that Ever and Simon, they can. What I know from what I read, it's is that 99% of the heavy metals in the water, they were trapped inside of this structure.
Of the crystals. Hey, Ever?
Yeah.
And you guys, maybe we could even hold questions for the very end. We just had a question from one of the students. What does the crystal actually do when you drop it into, say, a glass of water? How does it sequester the heavy metals? How long does it take? And then can you drink the glass of water? Is this like something that people could put in what they're actually drinking?
So the actual way that the crystals work is that the actual MOF, or the metal organic framework, has one ligand. It's actually constructed from two ligands if you look carefully at the structure. One of the linkers has a functional group. We call it a sulfone group. It's a sulfur oxygen based bond, and that type of bond actually has pretty strong interaction with soft metals. With soft metals, we're thinking of the large, like lead, mercury, those types of metals. So when we place it in the solution of an aqueous solution, what it does is all the atoms just interact and form an interaction between that functional group and the heavy metal. So then the amount of mercury that we can remove from the water depends on how much MOF we use as well, right? Because there's a maximum amount of mercury that MOF can pull out. I don't remember the specific details, but we measure that in an amount of like milligrams per gram. So for example, maybe 100 milligrams of mercury can be removed per gram of the MOF. As for drinking the water afterwards, in terms of heavy metal content, we show that this material can remove most of the water. It can bring the heavy metal levels below what the EPA requires. I necessarily wouldn't recommend drinking the water with the crystals in there. Probably some sort of filtration would have to happen after the MOF removes heavy metals.
Wow. Okay. And so the follow-up question was, how long does it take?
I can't remember. Give me 1 second.
Sorry. Oh my gosh. And Nedko, I'm so sorry. This just came in from a student. So we can wait. Tell you what, let's wait until the end of the we'll just wait till the end of the presentation. I'm sorry, Nedko, go for it.
Sure.
No, actually, I just was there that next inside of this project as a separate segment will be this musical composition that will be played by real musicians, and it will be part of, let's say, the promotion of this solution, of this crystal, of this great work. So that's the idea about the sounds here. They start. I should not put all of them together. But
hey, Nedko, one of the students wants to hear the heavy metal water too. Okay. Does it actually sound like heavy metal? Oh, that's great.
I want to say that this software that I use for generating these scales, these tones, it has not so much opportunity. This is like a regular piano. The final musical project will not have will have a piano, but it will be I don't know, violins, piano, whatever the composer will decide to use. Here the idea is that in a specific audience that is not, let's say, visual art audience, is not scientific audience, they will have this possibility to talk and to know about this and start like kind of making a little more noise about this discovery, about this crystal. So I can say that practically. Let me just go to the next slide here. I make something that is together, but it's still in very early stage. This project is let's say in the half of this. So it goes. It's a little monotonous, you know. It's like, but in the same way, the approach of this Baroque music with the forms and etc. I try to make this interesting for the audience, that practically. Inside of something so let's say not emotional, not something that is outside completely of any kind of art, of music. There's different approach, and this approach could be also effective for people to start thinking about the problem and the solution with the water. So sorry for being like a little bit.
Listen, Nedko, that was beautiful. I mean, as you were playing that video and the music, I could see like an immersive environment. Just beautiful, lovely.
Thank you. So that's actually in very fast my presentation. I will send this to everybody. If you guys want to see something or just give me some feedback, that will be nice. So I put that everybody that I really like to mention here, because I think that one of the most impressive for me was the possibility of this collaboration so far. And I think that without these guys there, there will be not possible at this moment to be in this stage. So I can answer the questions. I would like to see and to to hear the opinions of you guys, the young guys, of the scientists, and
absolutely beautiful. Okay, so tell you what, let's stop screen sharing for just a minute. Yep. Just so I can see everybody, just because when they start talking, their little our little windows light up. So hey, class, this is a pretty extraordinary. I'm going to turn. I had my video off. I keep worrying that my computer's going to crash while you're like doing your multimedia project. So hey, class, this is kind of amazing. This is a crystal that can take soft metal out of water, and we've talked in here about issues with lead, mercury, cadmium. Does anybody have any thoughts about the artwork? Any questions for the team? Anybody? By the way, thank you for the questions from you guys while the talk was going. I've got one more question from the talk. But did anybody else have any other questions? Don't be shy, guys. I remember I told you all to come up with a question, right?
What was the name of the software that you're using for the composition?
From the software for the for the sound, or the software for
for the sound, yeah, sorry.
I can send this to Professor Demaray later, because in the top of my head now I really cannot.
Yeah, well, listen, Nedco, if you forgive me, because I get like hundreds of emails. If you're okay with it, I'd love to give everybody actually, let's just have you put your email down in the chat at the end. Yeah, and then Kelly, you can email him. I actually was, Kelly, I was thinking about your projects as Nedco was playing his music. Actually, I had a sense that you would be interested in that. So one of the questions during the talk, and this might be for Ever or Simon or Nedco, how is the crystal made, right? We're interested in biodesign, so of course I'm sure everybody in here is thinking like, well, wow, how can somebody just go and make some of this themselves so that, you know, we can start purifying everyone can make their own water purification in an urban space.
Maybe I think I'll answer that.
Okay.
So a lot of these models are made through the self-assembly of metal ions with these organic linkers that we use. So actually, on the molecular level, they actually form coordination bonds between the actual metal ion to the actual organic linker. And most of these materials are made in high temperature reactors, or even things like vials. So basically, almost like you're baking these things in an oven for a while, and they'll precipitate out of solution. So typically, we'll grab a mixture of the metal ions and the organic linkers, dissolve them in some organic solvent. The most common one for MOF synthesis is dimethylformamide, and then we'll just heat it in the oven. Depending on the structure, different temperature ranges, you can go from 80 to 200 degrees C for some of these. And then we just wait. And we can then, depending on the type of material that precipitates out, whether it's just crystalline powder or single crystals, we can play with the conditions to get single crystals.
Okay, so it's a single crystal that you need to be able to do the uptake for the soft metals.
The uptake can be done with any morphology. So actually, for the uptake, it's preferable to have actual powder, because the surface area is larger and the kinetics, the rate of kinetics are faster. But in order to find out what the actual structure of the material is, we always require a single crystal. I mean, there's ways of doing it with powder, but the easiest way is to do it through through getting the structure solved by a single crystal.
So I'm just going to do a follow. So I think that the student question was, how do you make it? And my guess is they're asking, how do you make it? Because they want to know if like, your standard person living in Camden, New Jersey could make up a batch of this in their kitchen. How, is that pot one? Is there any conceivable situation where an individual might be able to make some of this? First question. And then my second question is, in powder form, how much water can you treat? Like how, just in terms of effort, if you're going to make up a batch of this, how much water can you treat over what period of time?
So in terms of making these, I mean, they're very easy to make, to be honest. At least once the conditions are found, they're pretty easy to make. The only thing or the only problem would be is if you have the materials. So to make these, we use very, very specific, like either for this MOF, I believe it was zinc nitrate. So you would have to have that specific chemical. And then the organic linkers for this are all synthesized. I think one of them is commercially available. As long as you have the raw materials, though, if you have the metal, the linkers and everything, it's literally just mix them together, let them dissolve and throw them into an oven.
Okay, so wait, so crazy question. You probably have to get the materials from like a chemical supply place, or are there things that, I mean, forgive me for my, are there things that you could like use around the house? Or are there sources that you might be able, might you be able to source some of these things from your immediate environment?
For this compound, no, you would have to get everything from at least the starting materials to synthesize the linkers from some sort of chemical supplier.
Interesting. Okay. And then the second question, if you have a powder, how much powder could purify how much water?
I don't remember the exact amounts. I can double check and maybe send you an email, but we have a way of measuring that. We usually measure like I said before in milligrams per gram. So based on the experiments, so this was another PhD student's work. We measure that amount in terms of milligrams per gram. So if this material can absorb maybe 80 milligrams of mercury per gram of material or something like that. It depends really, but that's usually how we get a range of how much it can absorb. And then the amount of time for this study, I think everything was done at 36 hours. I think Nate, which was the PhD student who did most of this work, he was going for maximum absorption of mercury. So leaving it in there a little bit longer would give him that. I didn't go over the kinetic work, but there might be some. I can send you an email to address those questions.
That's so beautiful. And then just one other, I mean, so I'm here. I mean, one of the things that I think is so beautiful about this project that NEDCO's doing, and by the way, any of you guys who aren't shy, just say something into your microphones, your box will light up and then you can ask a question. One of the things that I think is so fabulous about NEDCO and his project is that it really seeks to, what's the right word? To sort of memorialize this as a discovery, right? Like it's really pretty extraordinary that you can come up with this kind of a system that can pull these incredible, so like serious toxins out of the water for us. Who came up with this idea? Right. I'm sure that some amazing chemist was wandering around and went, oh, if I put these in this hot state, I link them with an organic linker, then perhaps I can pull, soft metals out of water. How did this come to be? What was what's the history behind this discovery?
So at the time when Nate was working on this, there was already other porous materials that were being used for the capture of heavy metals. But I think MOFs have a lot of interesting properties that can make them really good at certain applications. And the capture of chemicals is one of them, simply because MOFs, compared to other traditional porous materials, the other traditional porous materials would probably be like zeolites, if you've ever heard of them. MOFs can be tailored and functionalized through the organic linker or through the metal node. So if you have something that you want to capture and you can force an interaction between a chemical species and the actual functional groups, the chemistry of the actual linker, then you can target and capture those specific molecules. And with other porous materials, a lot of them, for example, zeolites, they're mostly based on metal oxygen bonds. So the tailorability of them is much more limited compared to MOFs.
Wow. But like, who came up with this particular, like, how did this idea, what's the history of, you know, what happened in the lab and how you guys came up with this, this structure?
I think so. This structure, I think Nate made this structure. So in our group, we've always worked on the capture of either metal ions or some sort of hazardous chemicals. I think he based this structure off a structure that was already previously published, and all he did was what we call is reticular chemistry. So we had a structure that had a very similar organic linker installed in it without the sulfone functional group that binds to mercury. So what he did is he replaced that linker and ended up getting a very similar structure that was porous and stable enough for these applications for soaking in water, because MOFs, a lot of them aren't stable in aqueous environments. So what he did is he based his structure, he based his structure off a structure that was already stable and just substituted a linker that was very similar to the one that was in the original parent structure.
Okay, amazing. So I have a feeling that as soon as Nedco, so Nedco, I'm feeling concerts. I feel like concerts are coming on. I know we've talked about this for a moment, like maybe in all of those different geographical places. And by the way, that chart is shocking. Guys, I don't know if you noticed the racial profile that was happening in each of those different areas. That's called environmental justice. We've talked about that in this class, kind of amazing. But I have a crazy question. I mean, when Nedco goes and does these performances, people in places like, you know, Dearborn, right? Or places that have like a lot of, say, lead in the water, which is so detrimental to children and neuronal development. Are they all going to go, hey, we want some crystals? Like, how do we crystals for the people? How do we get crystals to all of the people that are going to want them? I'd actually like to have each one of you give me your own answer. Maybe Nedco first.
One of the questions, one of the answers that I'm looking for, why things like this that exist are not applied, are not. So it's like 4 years ago that is actually designed this, correct? 4 years ago, approximately. And that's 800,000 people dead. I'm not saying that because with this we immediately will change, but
well, wait, hold on. That was waterborne illnesses. This is heavy metals like mercury and lead, right? Does waterborne illnesses include lead poisoning? It does. Okay, all right. So maybe not everybody, because I'm sure that there's all kinds of horrible stuff in the water, right? Like, you know, maybe
it's including this. It's including,
okay, all right.
I'm really looking for answers who and where we have to press socially that discoveries or possibilities like this, they start be used, they'll start be applied and give some solutions. Is there any, let's say, anybody interested in produce this ever? And Simon, you know something that is happening after that? That's one of my questions, actually, that
So I think maybe I can answer this. One of the biggest problems I think with the application of a lot of these MOF materials into real world applications is the scalability of these materials and also the cost of these materials. I think are the biggest drawbacks of these materials. There's a lot of work being done now on, and there's some companies that are starting to work on the large-scale synthesis of materials, because keep in mind, we do all these experiments, and even though in the lab we can design some of the most efficient materials for a specific application, it might not be feasible for large scale. One, because the synthesis is just too complicated for in a large scale.
So listen, everybody, complicated, it's complicated can also be expensive, right? Complicated can equal expensive. So that's one piece. All right, so go on.
And then the scale up part of it is a problem. Producing this material at such a large scale is definitely one of the problems. The crystallization process for a lot of these materials is very sensitive to the environment. So if you just try to scale up by increasing the concentration when you produce these materials, oftentimes you'll lead it'll lead to materials that aren't crystalline enough. So that means that the structure isn't forming properly. So that's definitely one of the drawbacks. The second drawback is cost. The linkers that we use in some of these materials, in some of these MOFs, might be quite difficult to make, even in the lab, and not to mention larger scale. So currently, I'm sure they have ways of trying to remove mercury from water, and they use what's as cheap as possible. They don't care about efficiency sometimes, as long as the cost is low.
Interesting. Hey, Simon, we haven't asked you. What's your thought?
Well, it's generally cost is the issue. If you think about the amount of water that you have to process, then you need to do it as cheaply as possible to make sure there's plenty of water. I know the lab. Part of one group in the lab somewhere at LBL, they're working on the processing of water as well, particularly the waters in Bangladesh, because they dug a lot of wells in Bangladesh, and then they've realized that they contain a high level of arsenic. Yeah. So they've worked out, they've got a relatively cheap process using electrolysis and iron, I believe, to precipitate out the arsenic. So they can do it at relatively relatively cheap amounts per liter, because that's the real problem. If your liter of water is going to cost even $1 to process, that's an awful lot of expense.
Yeah. So the other thing that I think is interesting, you guys, when you're thinking about biodesign, is that sometimes changing human behavior might be actually the easier thing. Like, wouldn't it be interesting if us Americans like identified our water source that was just for drinking versus our water source that was for showering or washing our cars or, watering our lawns. I mean, if you were to do that, then that liter of water, maybe you could afford, maybe that could be the liter that you drink. Class, everybody, I want you to think about this, right? What are the ways of potentially bifurcating those kinds of water sources? I know that in the Northeast, when it rains, in the northeastern part of the United States, when it rains, you get all kinds of horrible contaminants that are coming down through the atmosphere. Maybe there's some way that we could be saving just rainwater and then treating it for just the things that we're getting out of the, I don't know. Class, I'm going to kick this to you, but I want to talk about the art part of this now. We just did the science part. I want to talk about the art part. Hey group, I have a lot of art majors in here. I've got some intermediate majors, which is art. Does anybody want to talk about the art part of the project? Was there anything that you saw that NEDCO presented that you went, whoa, or did it give you any ideas, or do you have any responses if you were, say, a viewer and you were to go to one of these, to one of his, I'm going to say NEDCO exhibition performance, exhibit, what would you even call it? Would it be a gallery exhibition? It'd be a performance. There might be some kind of public participation. How do you envision what this is going to be on the ground with people?
Most probably it will be all of this. So we'll be in different places where we can, I will show some of the installations in place physically, videos, video projections, and etc. But then, as I said, concerts will be talking about introducing all the project with all the collaborators, and then start talking the same what we're doing here, because this is part of the project. So what we're doing today is part of the project. And so I'm still in the process to make this organization, because it's still the project is not finished as project itself. So then I will try to contact every possible let's say gallery or media that can spread more the and I think that as Evan Simon said, that the price is too high for the time being, because at this moment price is more important, the most important part of this. But there will be time when the price will be not so big, because the conditions will go so bad that that there will be. So it's the same like with any other problem, that we are waiting until the last minute that everything goes.
Well, I want to just say something, which is that if you are somewhere and you've got a lot of mercury in your water, and this is potentially something that some kind of treatment that you could do yourself at home in your own kitchen, $1 per liter is a pretty good deal, right? You don't have to put it in plastic. You don't have to, it doesn't take the effort to ship it somewhere. I mean, I am hearing that you need a filter, that you don't want to drink the crystals, but were you to do some sort of a treatment and filter it, and then that's the water that you drink, I could easily see, right now, I could easily see somebody doing that. And I also, the other thing that I think is kind of wonderful is that as an artist, Nedko, you've got so much at your disposal in terms of letting people know about this, right? I mean, maybe part of your installation is a ritual where people come to your space, and maybe they mix the crystals into the water, and maybe they pour it themselves. Maybe it's like a tea ceremony, right? Maybe there's like a ceremonial kind of, I'm serious, that's how us humans learn. It's true. Ceremony is one of the ways that us humans truly deeply imbibe learning. And it's one of the reasons that it's so powerful, right? That's how human culture transmits information, and it's how we've been transmitting information before we became literate, basically, in our last 1% of our time on Earth. So yeah, I'm excited to see how, as an artist, you're going to do this. I have some other thoughts based on literally projects that students in this group and also in my capstone group are doing. But I want to kick this to my class. We're at 3 o'clock, by the way, you guys. So we're coming to the end of this. But group, do you have any thoughts for Nedko? Like, what would you like to see this become? I'm going to start calling on you if I don't have somebody raise their hand.
Guess what? I found out how to redeem the Morse code.
Amanda, go for it.
Well, I was so excited to see that you had an auditory component of this, because music is really like a universal language that can reach a lot of people. So it gets your point across really beautifully. And I like the vision of what you're saying, where it could go. I myself, I'm not an art major. My sister was, and so I've been taken to so many galleries that celebrate science and art in this way. And I would be so excited to see this in a gallery someday or in a concert. So thank you so much for sharing this with us. It was really incredible.
Thank you, Miranda.
I need to try something out.
Hey guys, anybody else? Any thoughts? Anybody? I do. I've got a couple thoughts, but I'm actually surprised because some of the people in here are also in my capstone group. Nedko, I mean, these are, by the way, those 3-dimensional models are absolutely beautiful. I wasn't sure if those were sculptures, the models that you made. I'm not sure if they're sculptures or if they exist in a virtual space so that we can walk around them. How are you envisioning that?
These are actually still in level of project. I'm exploring because I still have to go a little more. I want to combine the molecule with with the other molecule of the heavy metal water. So I want to make this composition like a really dramatic. So, and I'm still there. So these are some, let's say, sketches. Everything that I'm showing here is in a stage of sketch and it in a process. So yes, I think that there will be 3D, three-dimensional, maybe 3D printed. I'm still thinking.
So I want to suggest something. If you have 3D models, how about some virtual space where people can, you know, just dive in and interact. I have another question, and this is Simon talking about the patterns that these make. Nedko, are you using those patterns to make the music?
Actually, Simon sent me the chemical structure. It's inside of that file that the software opens. So you have a possibility to see the structure in form of data, and I copy it, and then I make this just introduce it there. I didn't touch anything there. I just produced this sound. So it was interesting for me because maybe it's interesting for them because they never imagined that they will sound in some way. You know, this exactly molecule will sound in some way, and this creates like much more euphoria around this. What is like much more noise about the importance, because I see in whatever these two scientists and their teams are doing, I see a great opportunity to improve the situation with the water. They're promising with their discovery. So I just think that this should be going outside from their circles and go to everybody. And then even if you said, maybe we'll not do anything, but people will start like thinking, oh, maybe one bottle of water is a little more than we think it is.
I want to make another. So all of you guys that are in the capstone group, do you remember the project that Reba showed us? It was a little interactive game that you can play on your phone. You've got these 3D models, right? You can drop them into, say, a virtual space or even a video game. I love the idea of like a person being the soft metal floating in the water. So you could be you could be the lead, you could be the mercury. And then maybe if you got close to these, you're going to get, sucked in and taken out. Maybe some sort of like, because I don't know, listen to me, I'm an old person, but the kids these days are playing a lot of video games. So I'm just gonna put that out there. One other thing that I think is really extraordinary. Everybody in this group, we've talked a little tiny bit about grant writing. Right now, the NSF is actually having researchers put artists and designers on their teams. And it's because everyone's requiring something called the TTP, which is transition to practice. And us nutty, crazy artists have a great, wonderful times thinking about how to integrate these things into the real world. How does it, a designer thinks about how do you actually use these crystals? What do you do on your kitchen table? How might you actually, make something that you could do in your own kitchen if you want to, purify your water and keep it out of your kids' mouths before it's been cleaned. One of the things I think that you did, Nedko, is just brilliant, because this is so wonderful to see an artist doing this. I love the fact that you called it Absorbsin. I'm not saying sin, I'm saying absorbs in, right? So it functions on both of those levels. It's absorbs in, it can suck it in, or maybe it's absorbs sin. I don't know. But I just love the fact that it can go either direction. I like how kind of slippery and poetic that is. And I don't know, Ever or Simon, I'm not sure if people in your lab are excited about being branded, but if you've got an artist working for you for free, I would totally just, and that's another thing. You also may want to do your performances for the people that are working at these labs. Maybe Ever, the next scientific symposium that you go to, maybe you want to bring Nedko with you, right? Maybe Nedko will do this performance. Those audiences love this. Those are really people that just love it when an artist or a designer or a performer does something that's focused on their research. So I'm so excited to see the ramifications of this. One last little thing I want to say before we break, and this is specifically to Sharon and Shannon, who are both doing 3D modeling. Nedco, what was the name of the software that you're using?
Actually, the software that I received is called CCDC. It's a software that is produced, and I'm used exactly Mercury, which is the 3D renderer.
Yeah.
And I use what he used. I use something that I see the work of Simon and the work of the lab, wherever is in charge there. So I just try to penetrate inside and see every single element of this and try to get inspired with that. I just want to add something for the kids. It's important. Everybody knows that coronavirus is not the scientific name of this. Everybody knows that. Coronavirus is because it looks like a crown, like a corona. So that was my idea to play with the name of this, looking for something that will be kind of poetic and could be like some that. So who knows? I mean, I want to use it in place of just the chemical situation, because the audience maybe will be more perceptive.
Yeah. Just long story short, Sharon and Shannon, this is 3D software for chemical compounds, scientific illustration, data visualization. These are a lot of things that artists that are working into in 3D imaging are going into. Nedco, one of the things that the class does is it really thinks about the way that we can use design and art to figure out how to live better in the Anthropocene, right? To consider all of these issues that we're dealing with right now, and to figure out, one, maybe how to continue life on Earth, but also how to critically and creatively engage these kinds of issues. So I also love the fact that first art piece that you did seemed really depressing. It's really tough not to get really depressing, or to just, it's really hard not to focus on that. And I think one of the best ways to do it is to critically engage these kinds of issues, right? To make things, to design things, to do what us humans are really good at. We're good at this. And I think that never let, never let a crisis go to waste, right? Our ecological moment is a crisis, but we should not let this go to waste, right? We need to focus on what we can do in the built environment, and often with pairing with the life forms that are around us, or utilizing the material world that's at our disposal. So I really want to thank you. That was just absolutely beautiful. I'm going to go listen to the music. That was a knockout. I want to go sort of float through those spaces. Ever and Simon, thank you so much for coming in today. I think I probably share your sentiment. I cannot wait to see what Nedco does. And Nedco, there may be people in this class that want to pair with you to do stuff. So, could you put your email in the chat right now?
I put it.
You did it? Okay, all right. So everybody go copy that. That's his contact information. And Nedco will be in touch. We've got this software at Rutgers. I want to support you. So we're going to figure this out. Okay, I'm really excited. All right.
Very much.
So we're coming to the end of class. Anybody have any last minute questions for our presenters today? Shannon, Kelly, Brian, Joshua, Sharon, anybody? No? All right, well, listen, will you all turn your microphones on? Everyone turn your microphones on. You can even turn your cameras on if you have the bandwidth. Turn your microphones on, and let's give our presenters a big hand, okay? Big hand, everybody. Woo! Jazz hands. This is my favorite on Zoom, is you can do jazz hands. Gorgeous, really nice. Thank you so much. All right, everyone. I got a recording of this if you want it, Nedco, okay?
Thank you, Elizabeth.
All right, my pleasure. Bye, guys.
Really a pleasure.
Thank you.
Total pleasure. Thank you.
Thank you.
Ciao.
Simon, thank you, Ever.
Bye, guys.
Great to meet you guys in live.
Thanks for meeting you. Ciao.
Ciao.
Bye.